Hi. So today we're going to continue talking about energy, but we're going to talk a little bit differently about it. We're going to talk a little bit about thermal energy here and how heat moves around. So we're going to talk about heat transfer in and out of systems so that you will start to understand that, when we have a system like the skater going through the skate park, um, some of that energy becomes thermal energy. Where does it go? We're going to talk a little bit about that right now. So, how does that energy leave the system? How does it move to the surroundings? What exactly happens? So, how does heat move through systems or out of systems is going to be today's topic. So, we're going to start with these three things here. We've got conduction, convection, and radiation. You may have heard some of these before. We're going to go through and just kind of briefly talk about how each of those things are related to heat. We'll start with conduction. Okay, so conduction has to do with particles directly bumping into each other. So let's say that we have some molecules or atoms and they are moving, right? Molecules or atoms or particles in the air or particles in anything, a solid, a liquid, a gas, anything. They're moving around in random directions and they're going to bump into each other, right? Now, when you heat up something, so let's say maybe you light a fire or you're near something that was heated, right? So if you light a fire, you're literally breaking down molecules. It's a combustion reaction, so you're breaking down molecules, right? So and particles. So as those things break down, the particles that are involved in that reaction are going to release a lot of energy, and that energy is going to get released into these particles. So if you increase the kinetic energy in a system, you're going to be increasing the temperature. Okay. Somewhere something's getting more energetic. Okay. That's how it works. Now, let's say that you increase the kinetic energy in the system here, and we have all these particles and they're moving around, they're bumping into each other. As they bump into each other here, let's try it like this. Let's say that we've got a particle here and it's warm, right? It's got more energy. It's going to bump into this particle, transferring more energy, which is going to bump into another particle, transferring more energy, which is going to bump into another particle, transferring more energy, which is going to bump into another particle, transferring more energy, right? So as you add energy to a system, the particles are going to bump into each other and they're going to kind of hand off. They're going to conduct that energy, right? So a good example of this, right, is let's say you've got a pot. Let's use a different color, something a little more bland looking. You've got like a pot of water, right, that's boiling, right? So we'll say down here there's like flames or whatever. Okay. This There's your fire. Okay. And so you've got a pot of water and it's boiling, right? So there's water in here and it's starting to boil. So you're getting some smoke or some steam, right? Steam it is rather. Okay. And you have like a metal spoon, right? And you put your metal spoon, different color, please. Metal spoon into the water. If you do this over not very much time, the metal spoon is going to start getting warmer, right? Because the atoms that are making up your metal spoon actually conduct heat pretty well, right? They allow for that energy to transfer through the spoon, and eventually it's going to be hot to the touch, right? You don't pick up a boiling pot of water with your bare hands unless you have a handle on it, right? And you're not going to put something into boiling water and then just pick it out with your bare hands on it most of the time, right? Now, a wooden spoon would be better, and that's why wooden spoons are used a lot in cooking, is because wood does not conduct heat as easily as metal does, right? So metal's a really good conductor of both heat and electricity for the same reason, actually. It allows for the particles to move easier. Well, actually, okay, slightly different reasons, but it's fine. Okay, so that's conduction, all right? It is through things touching, basically. Okay, convection is a little bit different. So let's expand our line down like this. Convection actually has to do with air particles or water particles in what we would call fluids, right? So this works in both the air and the water. Okay. And here's what happens. Let's say you've got a heat source, right? And from that heat source, there are, so we'll say heat source down here, right? So this is where our heat source is coming from. Okay. And from that heat source, it's going to warm up the air particles around it, right? Through conduction, right? So these particles are going to be getting more energy. And you'll see that they're pretty far apart from each other, right? Now, as you get farther away from that source, you might have a lot more dense air particles up here. And I'm going to fill in that gap with these particles as well. Now, these can be the same particles. They can be air particles, water molecules, whatever liquid fluid you're in, right? So remember, gas can be considered a fluid in this case. So what happens is this less dense packed space, less dense stuff tends to rise, right? Because we know that less dense stuff floats on top of water and less dense stuff rises through the gases in the atmosphere. So you heat up these particles, and as they get heated up, they're going to start to seek a higher place. They're going to start leaving. They're going to start moving because they're less dense. And the more dense objects, the blue stuff is going to start filling in the space behind it. And eventually, what happens is the more dense stuff is going to drop to the bottom, heat up, and then rise again, right? So let's walk through this just for a second, okay? If you heat something up, that heated up stuff is going to have more energy. As it gets more kinetic energy, the particles are going to move around more, right? So they need more space. So that means you're going to get less dense particles. And what happens to less dense particles is they rise, right? And the reason for that is because when you give something more energy, okay, in order for it to get less dense, it's going to have the same amount of mass, right? So let's say that both these areas have the same amount of mass, has the same amount of mass because density equals mass over volume, right? Same amount of mass is the same, but volume changes, right? It takes up more space. So you have less particles taking up more space. So a larger V for volume in this case leads to a less dense thing, right? So then as the particles begin to rise, they're going to start giving off some of this heat through conduction, and they're not going to be as close to the heat source anymore. So eventually, as they cool off and particles reach the top, this is where they're going to start getting more dense. Okay. And as they get more dense, you're going to see that density equals mass over volume. You're going to see here that the volume is going to go down. So as you decrease the volume, you can keep more mass in a smaller space, right? You increase the density. That's how this works. That's why this one has decreasing density, okay? And this one has increasing density. So as the particles, they get more energy and they rise, they actually start then losing some of that heat and then packing back together into a more dense thing, right? Which cools off, right? And as it cools off, it's going to drop again through, right? So here in this conduction process, this is kind of how we do our air conditioning and heating systems, right? We rely on the idea that okay, heat rises and cold sinks, right? So we know that to be true, and the reason is because of this description of conduction right here. So heat rises and cool sinks. This works in the ocean. This works in your house. This works in the atmosphere. This convection is a driving force of a lot of our weather patterns and things like that. And it also helps to kind of heat our homes and things like that, right? So it's probably warmer on your house on the second floor or in the higher places of your house than it is in the lower places of your house because of this convection idea. Okay, so let's move on to radiation. So radiation is giving off electromagnetic radiation, right? So um, as particles accelerate, charged particles, as charged particles accelerate, they give off electromagnetic radiation. Okay. Now, let's talk a little bit about what that means. Oftentimes, we see this literally as visible light. Remember, light is energy, right? So, when you're looking at a fire, looking at a fire like this one, bear with me. I'm going to draw it very specifically because I want you to see something. There we go. And I don't know, we'll put like a log or something down here, right? There you go. We've got a log. It's on fire. Hooray. Okay. When you're looking at a fire, you're literally seeing, right? You can see this stuff, can you? You can see this light being given off by this combustion reaction, right? So we're basically breaking down the particles in this wood, right? And as those particles are breaking down, they're giving off energy. A lot of that energy is just felt as heat, right? Through conduction, right? It heats up the air around it and then it convects, right? So that air is going to end up going up and rising, right? And then the cool air is going to be coming down, right? The sides, right? And a lot of that air is heated up near the fire by conduction. So you see, you can tell where conduction and convection are happening, right? That's the stuff that you mostly make sense to you. But you can literally see with your eye the light from the fire, right? That light itself is the energy that's given off through this radiation process. Okay, so that's electromagnetic radiation. Now, what's interesting about that is let's put some cold air between you you and the fire, right? You've probably stood by a fire. You're a human being. You can still feel warmth getting to you somehow, right? That warmth that gets to you, even though there's cold air around you, is coming through the cold air as electromagnetic radiation. And that causes you to feel warm, right? Because what happens is as these particles get excited in these reactions, charged particles which make up your atoms, right? The atoms that are around in the air, in the wood, the fire, right, is going to cause some of that stuff to break down. And as those particles start to move, like electrons are shooting through the air, right? Protons are shooting through the air. When those charged particles accelerate and they hit new surfaces, they're going to transfer energy in the same way that conduction and convection transfer energy. So conduction is particles bumping into each other, right? So like your atoms bumping into each other and transferring energy through collision. Similarly, a charged particle is going to transfer energy by traveling through space, and then colliding with you, right? So you might feel a charged particle. Well, you're not going to feel the particles hitting you, right? But you might feel warmth, and that's because energy from the fire is being transferred through electromagnetic radiation to you. And radiation is complicated, okay? And we're going to talk a little bit more about what waves do later on, but this is really the basics of it, okay? So what we're going to do now is we're going to come up with some examples of each of these.